Hello and welcome to today's lesson on Alpha Decay. Here's what we will cover in today's lesson. First, we will learn about the properties of alpha decay and the kinds of nuclei it typically occurs in. Then, we will delve into writing nuclear equations for alpha decay. Up to now, we have explored the concepts of radioactivity and the idea of half-life. You are familiar with why some nuclei are unstable and how they undergo radioactive decay, emitting different types of radiation to become more stable. With this understanding, we can now dive deeper into the types of radioactive decay. Radiation comes in three primary forms: alpha particles, beta particles, and gamma rays. Each type of radiation is unique in its composition, energy, and the way it interacts with matter. In today's lesson, we will focus on alpha particles. An alpha particle is essentially a helium-4 nucleus, which includes 2 protons and 2 neutrons. Because it has 2 protons, an alpha particle carries a +2 positive charge. This charge, along with its relatively large mass compared to other forms of radiation such as beta particles or gamma rays, gives alpha particles distinct characteristics and influences how they interact with other materials, as we will explore in upcoming lessons. When an unstable nucleus emits an alpha particle, it undergoes a transformation in both its atomic number and mass number. Since the nucleus loses 2 protons, when it emits an alpha particle, the atomic number decreases by 2. This change alters the element's identity, shifting it to a different position on the periodic table. Along with the loss of 2 protons, the nucleus also loses 2 neutrons, totaling 4 nucleons. As a result, the mass number decreases by 4. Alpha decay typically occurs in heavy nuclei that have an excess number of protons and neutrons, which makes them unstable. These nuclei are often found in elements with high atomic numbers, such as uranium or radium. To reach a more stable state, these heavy nuclei emit alpha particles, thereby reducing their atomic mass and achieving a more balanced proton-to-neutron ratio. It's also important to note that the emitted alpha particle carries kinetic energy, which is a part of the overall energy released during the decay. This energy release also contributes to the stability of the resulting nucleus. Now that we understand the properties of alpha radiation, let's see how we can represent it with equations. A nuclear equation represents the changes that happen within the nucleus during radioactive decay. It is similar to a chemical equation, but focuses strictly on the nucleus and its components, namely protons and neutrons. Let's take the alpha decay of uranium-238, often written as U-238, with an atomic number 92 as an example. Our first step is to identify the original nucleus. Uranium-238 has a mass number of 238 and an atomic number of 92. In nuclear notation, we would write this as shown. Next, we need to understand the emission process. An alpha particle consists of 2 protons and 2 neutrons. This emission causes the original nucleus to decrease in both mass and atomic number. The third step is to apply the conservation of mass and atomic number. In a nuclear equation, both the mass number, the total number of protons and neutrons, and the atomic number, the number of protons, must be conserved. This means that the sum of the mass numbers and atomic numbers on both sides of the equation must be equal. Let's start with the mass number. Uranium-238 has a mass number of 238. When it emits an alpha particle, which has a mass number of 4, the remaining mass number for the new nucleus will be 238 minus 4, which equals 234. Next is the atomic number. Uranium-238 has an atomic number of 92. After emitting an alpha particle, which has an atomic number of 2, the atomic number of the new nucleus will be 92 minus 2, which is 90. With the new atomic number of 90, we can identify the element that forms. Using the periodic table, we see that the element with an atomic number of 90 is thorium. Therefore, the new nucleus formed is thorium-234, written as shown. Now that we have all the pieces, we can construct the nuclear equation for the decay of uranium-238. uranium-238 decays into thorium-234 and an alpha particle or helium-4 nucleus. When written out, it should look as shown on the whiteboard. Let's try another problem. We need to write the alpha decay equation for radium-226. The first step is to identify the initial nucleus and its properties. Radium-226 has an atomic number of 88. Next, we determine the changes after emission. When radium-226 emits an alpha particle, it loses 2 protons and 2 neutrons. Therefore, the mass number decreases by 4, which would be 226 minus 4, which is 222. The atomic number also decreases by 2, which is 88 minus 2, which equals 86. Step 3 is to identify the new nucleus. The element with atomic number 86 is radon. Therefore, the new nucleus is radon-222. When written as a nuclear equation, it will be radium-226 decays into radon-222 and an alpha particle. Let's try a final problem. We need to write the alpha decay equation for polonium-210. As always, we first identify the initial nucleus and its properties. Polonium-210 has an atomic number of 84. Now we need to determine the changes after emission. By emitting an alpha particle, the polonium-210 will lose 2 protons and 2 neutrons. From this, we know the mass number decreases by 4, which is 210 minus 4, which equals 206. The atomic number decreases by 2, so will become 84 minus 2, which is 82. With this information, we can identify the new nucleus. The element with atomic number 82 is lead. Therefore, the new nucleus is lead-206. So when we write the nuclear equation, it becomes polonium-210 decays into lead-206 and an alpha particle. In today's lesson, we explored the properties of alpha radiation and its role in alpha decay. We established that an alpha particle is a helium-4 nucleus consisting of 2 protons and 2 neutrons, making it relatively large compared to other forms of radiation. We understood how alpha decay primarily occurs in heavy nuclei that have an excess of protons and neutrons, leading to instability. We also discussed the energy released during this process, as the emitted alpha particle carries kinetic energy. To illustrate these concepts, we practiced writing nuclear equations for alpha decay. In summary, understanding the properties of alpha radiation and how to write nuclear equations for alpha decay provides a deeper insight into nuclear stability, radioactive processes, and atomic structure. This knowledge is fundamental to our broader study of atomic physics and nuclear reactions.